Hi everyone, my name is Konstantin Vladimirov, and we are in the third lecture of our master's course in the C++ language. And in the last lecture, we covered the first fundamental building block of generic programming, generic classes, using std basic string as an example. Today, we move on to the second such block, equally important, the overload set. It is the skillful use of function and method overloading that allows us to create truly universal and convenient interfaces. Before diving into technical details, let's recall the essence of generic programming. You may see on this slide the quote of Alex Stepanov, one of its pioneers. The first step is to get the algorithm right. The second step is to figure out which sort of things, types, it works for. It's important to understand that first we get the algorithm, and second step, we determine the types. These types are not invented out of thin air, but are rather discovered during the design process, flowing from the very essence of the algorithm. Let's take a concrete example. Raising a number x to the power n. The simplest, most naive algorithm is to run a loop from 0 to n or from 1 to n and multiply x by itself on each iteration. Pause the video now and try to propose a better solution. Imagine you are on job interview. 3, 2, 1. Okay. And indeed, a much more efficient algorithm exists, the so-called exponentiation by squaring. It's based on the binary representation of the exponent n, here, and solve the problem in logarithmic time, which is critical for large n. The algorithm uses a loop, this one, that cleverly halves the exponent and squares the base on each step. And on each step, this algorithm checks the least significant bit. This is the check to know when to multiply the accumulator. Now let's ask the second question of generalization. How do we make this algorithm universal? How do we adapt it to work not only with integers, but also with other data types? How would you do it? Okay, the first impulse is to make the function a template, simply introducing a type parameter t instead of specific unsigned here. Here was unsigned and return unsigned, and here we have t, here t, and there t. And we replace the accumulator type with t. And we hope that's enough. But let's look closer. Do you see any issues with this approach? And I believe you do. I personally can see even two issues on this slide. And first issue is rather obvious, because even if t is something integral, if t is signed, this check is pure madness. What's wrong with raising to power 10 minus 2? Okay? Minus 3, minus 4. X less than 2, what it really means? It means that we want to compare x to accumulator. If x is equal accumulator, then return x. Okay. And main question, what exactly is t? For which types does our exponentiation algorithm even make sense? We can name integers, okay, floating point numbers, okay, but what if I want to raise matrices to a power? Indeed, the algorithm doesn't change if t is a matrix. Okay, do you see it? Great. Immediately, the initialization problem arises. what will be the neutral element our 1? For a matrix, it's the identity matrix. And for the scalar like 1, will we implicitly convert the scalar 1 to an identity matrix? And for the scalar 2, will we then provide an exception or maybe undefined behavior? And this is important. This is how we learn to design programs correctly. Generalization is not just type replacement, it's thinking through the semantics of operations for those types. One possible solution for this identity problem is to assume, and note I also fixed the second bug, is to assume that a global function ID exists for type T, returning the neutral element. However, this is very strong and really non-standard requirement that severely limits the universality of our algorithm. Generally, requiring global function without a specific namespace is only possible if their names are very well known. You can require begin to exist somewhere, okay? Begin existing everywhere. But asking for ID is probably too much. What else can we invent here? Okay, in the last lecture, we talked about type traits. Let's try type traits. So another solution here is to introduce additional template parameter, a trait, for example, default ID trait of T, and initialize the accumulator with the value trait : ID. Who likes this idea in this audience? As the raised hands show, not everyone. And for good reason. If we look at the standard library, at the signatures of algorithms like accumulate, transform, or copy, we don't see traits in them. This is not an argument from truth, but from style. Such an approach is not idiomatic to the C++ standard library. A better solution consistent with the spirit of STL is to pass the initial value for the accumulator as a function argument. This way we separate the pure, efficient algorithmic part from the initialization problem, shifting this initialization problem to the caller. And this approach aligns well with the philosophy of the standard library. Algorithms in it are designed as clean rooms. They do not check their input parameters for correctness, and in the most algorithms of standard library, incorrect parameters lead to undefined behavior. All the work of ensuring correctness and preparing data is done by a user wrapper function. For example, the same ends power wrapper function. It can already take care of proper initialization, for instance, using 1u for unsigned types, or check against 2, which is normal again, because we are in the concrete function, and so on and so forth. And if we will look here, what do we see at this slide? At this slide, we already see an overload set. And here we come to a key conclusion. The second fundamental building block of generic programming is overload set. This is not one single generic function, but a whole set of overloaded functions, constructors, operators, and methods that together form a single flexible and powerful interface that we can refer to using the single name. For example, the name and power. It is the skillful combination of overloads that allows us to create truly universal and convenient code. And let's consider a concrete example from the standard library, the comparison operator equal for stud basic string. A naive implementation might look like this, might look like comparing two basic strings via the compare method. And what's wrong with it? Imagine a situation when one of the operands is a string literal, const char pointer, or something like this. In this case, an implicit conversion of this literal into a temporary basic string object can occur, which is inefficient and can lead to unnecessary memory allocations, which of course we want to avoid. What to do here? Please give me some suggestions. 3, 2, 1. Okay, and of course, a better approach is some solutions that really exists in libstd++ is to provide an overload set for the equal operator for various type combination. Basic string with basic string, const char pointer with basic string, basic string with the const char pointer, and so on. This avoids unnecessary conversions and ensures maximum efficiency. This is exactly how it's done in the standard library, though in reality an even more clever mechanism using basic string viewing is used there. You can see that here we even changed the order of arguments, and here we are calling right hand side dot compare of left hand side, and here we call it left hand side dot compare of right hand side. Okay, equality is symmetric, it's okay. So we can see our first examples of overload set, and we like it. It's good overload set. And let's now generalize the question. We generalize types, generalize algorithms. Can we generalize questions? Are there any general principles for designing an overload set? How to distinguish a good overload set from a bad one? And here's a light-hearted rule of thumb. A good overload set is one you wrote yourself. A bad one is one written by someone else. What can we propose aside of this rule of thumb? And let me show you just some examples of good design, and let's examine them because it is important. First, this is overload set for different but related types. We have two foo functions. One takes a const char pointer, the other takes a string. The key here is that the string overload delegates its work to the const char pointer version by calling cstr method. This ensures consistent behavior and avoids the inefficiency of the compiler creating a temporary string and so on and so forth. Second, overload for different number of parameters. Consider a twine function, a hypothetical string builder. It's convenient to have overloads that take a varying number of arguments, so user can call twine with hello and name, or hello name space surname, and so on. The overload set provides a flexible and intuitive interface for the same core operation, building a string, without forcing the user to pack arguments into a container manually. And third, for optimizations, because I shall repeat it once again, C++ is for performance. And the studVector pushback method is a classic example. It has two overloads, one that takes a const tref, an value reference for copying an existing object, and another one that takes a tref, an value reference for moving a temporary object or an object explicitly marked for moving with studMove. This allows the vector to efficiently handle both cases, avoiding expensive copies when possible. Okay, what we can squeeze from those three examples? And there is one really smart engineer, Titus Winters. He works for Google, I believe. And in one of his talks, these talks will be in my bibliography, Titus Winters formulated excellent rules for designing overloads. I call them Winters rules. First, you should not force the user of your code to perform complex overload resolution in their head. In the next lecture, we will see how complex overload resolution can be. If deep understanding of C++ rules is required for correct usage, the design is likely flawed. Second, the entire overload set should have a single clear purpose that can be summarized with one brief comment. If different overloads need different comments, that's a bad sign. Third, and this relates to the first point, every element of the set should do roughly, I want to emphasize, roughly the same thing. The behavior should be uniform. Personally, I think the third is the main one, because second and first are just corollaries of the third. And here I can show you a stark example of a bad overload set. It is a function, list coprime, with one name, but completely different semantics for different argument types. Imagine, for an integer it finds the smallest coprime number, and for a string parses it and returns some number. Using such an interface is pure torment, and you see it described with like one comment, but this comment is really two comments in disguise. Okay, and now when we know the rules and we are sure, we will look into the standard library and we will find something great, something we can teach, like teach ourselves of perfect C++ code from standard library overload sets, do we? Okay, let's look at this transform overload set from the standards library. Let's apply these principles to a real-world example. And here we see its main overload set. We have the first overload, which is the classic map operation. In functional languages like Lisp or Haskell, it is definitely map. It takes one input range, applies an unary operation to each element, and writes the result to an output range. Then, the second overload is essentially the same map operation, but it adds an execution policy to allow for parallel execution. But then, look at the third overload. This one takes two input ranges. It applies a binary operation to pairs of elements from these ranges. In many programming contexts, this operation is known as not as map, but as zip. It like zips two sequences together with a function. So we have to ask ourselves, is this a good overload set? According to Tedious Winter's rules, this might be questionable. The problem is semantic unity. Can we describe what std transform does with one brief comment? It's difficult. Is it applying an operation to elements from a range? That fits the first two, but fails for the third, which requires two ranges. Is it maybe applying an operation to elements from one or more ranges? That becomes like vague. And one could argue that under a very abstract definition, transform a range or ranges using an operation, it holds together. And there is a historical convenience to having the zip operation under the familiar transform name. However, from a pure design perspective, this is a point of criticism. We are effectively merging two distinct algorithmic concepts, map and zip, under a single name. This can be seen as a violation of the principle that all overloads should do roughly the same thing. It's not a hopelessly bad design, but it's certainly a controversial one, and it serves a good example for discussion. What are your thoughts? Write down in comments what do you think about such designs. Does this feel like a single unified operation to you, or two different ones bundled together? Okay, let's go on and let's look at another real world example that really, I would say, pushes the boundaries of a large overload set. The constructors of stud basic string. And as you can see, this list is extensive. We have constructors for almost every conceivable scenario. Default construction, creating a string from a character, character repeated count times, copying and moving from other strings with optional positions, constructing from C-style string, with or without specified length, from iterator ranges, from initializer list, and even from string view-like objects. On the one hand, you have to admire the flexibility. The positive way to look at this is you can create a string from practically anything. This interface is a powerhouse of convenience. But on the other hand, this incredible flexibility comes at a cost. Such a vast and diverse set of constructors can be a source of subtle errors. The classic example is the potential ambiguity with integers. If you accidentally pass a single integer like 0, the compiler might interpret it as a null pointer that fits into this overload, leading to undefined behavior instead of clear compilation error. And this is a direct consequence of having so many conversions path available. So is this a good overload set? And I would argue this is a trade-off. It provides immense utility, but demands a high level of awareness from the C++ programmer to avoid its pitfalls. It's a great example of how large overload set can be both incredibly useful and incredibly potentially dangerous. Okay, the key to creating good, predictable, and safe overload sets is the explicit expression of requirements for types. We need to explicitly specify which types are allowed and which are not. And here, mechanisms for modern C++ come to our aid. Concepts and requires clauses. On this slide, you can see a requires clause. Requires clause is a mechanism that allows specifying requirements for template parameters at the compile time. If the requirement is not met, the function is excluded from overload set, and we get a clear error message. Not miles on incomprehensible compiler output. This makes our code not only more reliable, but also much more friendly to those who will read or use it. And we can see that if we have this check equality function, it is better to have check equality function requires this is equality comparable, because we are really using here equality comparable, because we may check equality for types that are not equality comparable. For example, if we have just less, then we can use less operator inside check equality function. Okay, and the beauty of requires clauses lies in their flexibility. We can combine several requirements, here forward iterator and totally ordered, and the compiler will clearly indicate which one exactly is not satisfied. This is much better than old good Sphere, which we will look at later, but which often resembles some magic. Here, no magic. We have two clear requirements, and both clear requirements can be satisfied or not. Moreover, using requires, we can create overloads specialized for specific categories of types. For example, one function like for integral types, and another function for floating point types. And if we try to call such a function with some type that doesn't fit into any category, how do you think? What do we get? Please think. Don't try it in good bold, because it will be too easy. 3, 2, 1. Okay, hope you paused the video and give it a try. And okay, if we try to call foo with a type like our custom struct S that satisfies neither constraint, this is where the real power of requires clauses shines. The compiler doesn't just give up with a cryptic no matching function error. Instead, it helpfully examines each candidate and tells us why it was rejected. As you can see, the error messages are clear and informative. For each overload that was considered, the compiler prints a note saying constraints not satisfied, and then specifically shows which Boolean expression evaluated to false. In this case, it clearly states that both studies integral and studies floating point are false. This is a massive improvement of the old template error messages, which we will look at later. Instead of a wall of text, we get a direct point-by-point explanation of the failure. It makes our code not only safer, but also much more user-friendly, guiding the programmer directly to the root of the problem. Okay, and absolutely, this is a slide that explaining why in some cases, absolutely we have this slide that explaining why behind the mechanism. In some cases, we can even achieve complete coverage of all possible types using requires. For example, one overload for types with a size greater than 4 and another for size less or equal than 4. This is a powerful tool for creating exhaustive and type-safe interfaces. But this might make you wonder, why does this even work? After all, if we look at signatures of those two functions or at mangling of those two functions, we will see that those two functions are the same. These are both templates with a single parameter t and both take a single argument of that type. In a world without constraints, this would be a redefinition error or a clear ambiguity. The key is that requires clause have a special status in the language. According to the C++ standards, two function templates, and here's quote from standard, are considered different if their constraints are not equivalent. Or standard states it vice versa. Two-function declaration of the same name refer to the same function if they are in the same scope, have equivalent parameter declarations, and equivalent requires clauses, if any. The compiler treats the requires clause as an integral part of the function's interface, but not functions mangling, for the purpose of overload resolution. So in our example, the constraint size of t greater than 4 is fundamentally different from size of t lesser equal than 4. This tells the compiler that these are two distinct function templates that just happen to share the same name. When you call foo and pass some value, compiler looks at the type of value, evaluates the constraints for each candidate, and only the one with the satisfied constraint is added to the set of viable overloads. And we will speak about viable overloads in more detail in the next lecture. This is what allows us to create such clean, non-ambiguous, and exhaustive conditional interfaces. And it's important to understand that functions with the same name and signature but with different requires clauses are considered different functions. And potential danger lurks here. If the requirements are not mutually exclusive like this, these requirements are not mutually exclusive. These are the same. An ambiguity in the call might arise which the compiler will be obliged to reject. And these don't even require compile time evaluation. Those are the different functions, and both functions are viable overload candidates. Okay, so beware of this. Okay, and simple requires clauses have their own problem. Imagine we created um, two like sphere. The Imagine we created two functors for usage inside the requires clause. First is input iterator and second is random iterator. It's logical to assume that random access iterator is a specific case of an input iterator, but for the compiler, these are just two independent Boolean expressions. If we create two function overloads based on this, then for a random access iterator, the compiler won't be able to choose the best overload because both requirements will be satisfied. You see, if I try to use here requires clause and here requires clause, for me, it is logically correct. It is crystal clear what I'm trying to say, but the compiler cannot understand it. We need to somehow explain the hierarchy of our requirements, their nestedness to the compiler. To solve this problem, we need more expressive means. Requires expressions and concepts. Requires expressions allows checking not just the value of a Boolean expression, but the syntactic correctness of an expression for given types. For example, this is requires clause and this is requires expression inside the clause. And this requires expression checks if the comparison operator equals exists for types t and u. Using requires expressions gives even clearer error messages. Instead of a dry requirement not satisfied, we might get a message like because t equal u would be ill-formed or invalid, which immediately directs us to the heart of the problem. And the main difference between complex constraints like requires expressions and simple ones like requirements is that simple ones are evaluated as Boolean expressions. Here we have requires clause and it is evaluated in compile time and okay, it evaluated to false. While complex ones check the syntactic correctness of operation. Can we compare result of some pred with 42? Of course we can. This is a fundamental difference that gives concepts their power. And here, this will be dropped from the overload set and this will stay at the overload set. But this is not evaluated. This is only checked for correctness. Okay, and now let's look closer at the syntax of requires expressions. We can check simple expression like u plus v does it compile correctly. We can check the existence of nested types like type name tinner and think of each requirements inside it as a conjunct, because this requires expression is true if and only if this is correct and this is correct. The result of this expression is logical AND on results of those two expressions. And there are two more types of requires expressions. Those are simple requires expressions, those are type requires expressions, and we have also compound and nested requires expressions. But before we will go into the compound and nested expressions, let's try to make some free write because writing long requires expressions directly in the function declaration can be tedious. This is where the concepts come to our aid. A concept is a named set of requirements, essentially an abbreviation for a complex requires expression. We can give a clear name, like here, convertible to our set of requirements and use it later in our code, making it significantly cleaner and significantly readable. The standard library provides a rich set of ready-made concepts like stud integral, stud floating point, stud convertible to, by the way, because this example is from this CP reference page, and many others. Using them is good practice as they are standardized and familiar to other programmers. And you may just think that if you can see concept, that concept is abbreviation of complex requires expression with maybe some Boolean expressions, and all these are packed to the single concept. And of course, you can check a concept not only inside requires expression. It's important to understand that a concept at its core is a compile time predicate. Like here, stud move constructible from S. It's a tool that answers a question about a type with simple yes or no, a Boolean value. And because it's value, you don't need to call it like a function. The concept name itself is a value. You don't need to make stud move constructible : value, or maybe stud move constructible like braces or so. And you can use a concept directly here in static assert to enforce requirements right at the point of declaration. And this, using concept inside static assert right at the point of declaration, is an excellent practice for validating assumptions in your code. Every time you're writing forward iterator, please static assert stud forward iterator from your type of iterator. But that's not all. Since it's just a Boolean value, you can even assign it to Boolean variables or to compile time Boolean variables. This can be useful for complex conditional compilation of a storing the result of a concept check for later use, and it really emphasizes that concepts are first-class citizens in the type system working seamlessly with other compile time constructs. And we already mentioned the compound requirements. Compound requirements allow, this is the compound requires expression, allow checking not only that an expression compiles, but also that its result has a certain type or converts to it. This expression compiles, and its type converts to, its type is certainly this one. And this one compiles, and its type is convertible to this one. As well as the expression doesn't throw exceptions. This is compiles, and this operator plus plus increment operator shall be marked no except for this constraint to be satisfied. And last but not least, we do have nested constraints, because sometimes inside a requires expression, you want to evaluate some expression, and requires expression are not evaluating anything, but nested requires expression do. You have requires expression. Inside it, this requires is just a nested constraint. And now size of at t equals 4 is calculated, and some predat c equals 42 is calculated, and no except is calculated, and so on. And let's play some game. Please look at this requires clause. This is really interesting requires clause on this function template. And please try to simplify it. I will take you some time. Please pause the video now and try to simplify it. 3, 2, 1. Okay. And we can drop this one and this one. This is just requires no except what plus t. No except for plus t. Although it might seem cumbersome at first glance, in practice it is a powerful tool for expressing complex conditions. So now you know all 4 types of requires clauses, and let's talk a little bit about constraints. Constraints on concepts. There are 2 limitations. One limitation of concepts is the prohibition of explicit recursion in their definition. The compiler will not allow a concept like this, like all true, to refer to itself directly, like use all true here. This is prohibited. And also, you cannot constrain the concept definition with other constraint. You may constrain any template except concept definition. I believe those 2 limitations were introduced to exclude possible Turing-complete programming on concepts. Because in languages like Haskell, we do have type classes, and you can write Turing-complete programs on Haskell type classes, and if we will allow this for C++ concepts, we will have not only a single source of metaprogramming, but 2 sources of metaprogramming, and I believe committee just wants to avoid this. And this is critical, and this is not so critical, because this limitation, what does it mean? I want T to be inner, to have some member called inner, to be inner of T. And can I express this somehow different way, in some different way? And of course I can. Of course, I may just use conjunction, and this concept says explicitly this must satisfy these concepts and be something else. So I just circumvented with just conjunction, and it is really easy. And for using concepts in your code, we will have several flavors of concept syntax, and syntax is really diverse. Basic syntax, as I call it, is using explicit requires clause on function. This might be requires clause here, or this might be trailing requires clause. Trailing requires clause might be more convenient if you want to operate with function argument names. You do not have function argument names here, but both clauses before function name or trailing clauses are basically the same. And you may abbreviate it. You may use template parameter like student integral here, and if this is concept, you can constrain with concept here instead of type name. And what is more important, you may even not write template here. You may just write student integral auto, and this is still a function template. And this T is constrained to be student integral, and this is like regular function template that can be instantiated and so on and so forth. And also you can do this with local variables. And I believe that this is the only way to use auto local variables properly, because this is not only makes the code safer, it documents it. If I'm saying just auto x, I'm saying too much. What I want here is to say x is automatically reduced, but this x must be integral. This must obey some contract. And this is a concept that tells me this if I'm like reading this code, okay? And also you can restrict a class template. You can have requires close this, and as you guess, you can have a concept here and so on. And the most funny of this abbreviation, and it is curring or partial application. We can create a new concept by like fixing one of the arguments of another concept. For example, the concept stood same as t int may be abbreviated as the stood same as int of t, and this t will magically jump here just in the beginning of the parameter list of the concept. And that is why, let me show some slides back. That is why, like this worked, because what do we have here? We have convertible to, but convertible to have two arguments. And what does it mean? This means that type that was deduced here magically jump in the beginning of the list of stood convertible to concept. So carrying from the backward, any new carried argument jumps into the beginning of the list. Okay. Let's go deeper. Can you constrain member functions? And of course you can. And constraining member functions is really a funny technique, because this allows, for example, providing certain methods only when the class satisfies some requirements. Like you may have some class that have empty method only for types that, like here, this class has empty method only for types that are modeling forward range concept. And if D is not a forward range, if it is like input range, what is an empty input range? I don't know. Empty is for forward ranges, for bidirectional ranges, for random access ranges, and this method just not exist if this is not forward range. And this method is even trickier. This method checks that method empty of this value and requires that this method exists. And there is one really bad idea. There are some proposals in standard like requires auto. What does it mean requires auto? This means please look up all the function body, all expressions, and let's require that all expressions are true to make this function exist. And this is a really bad idea. It leads to extremely fragile interfaces if implemented, because you need to document your intent as a part of function signature. It is madness to deduce it from function body. I hope this idea will never be the part of the standard. And if we can constrain member function, what is the next logical step? Okay, you know it. We can constrain constructors. And constraining constructors is like really crazy. We can apply constraint to the type as a whole. This foo class exists if and only if this t have foo method in it. Okay. But for any constructor, we can apply additional requirement. This constructor requires default initializable t. Otherwise, it does not exist. This constructor requires copyable t. Otherwise, it does not exist. Please write in a comment. How do you think? For constructors, requires auto a good idea? Because this looks like a boilerplate. Yes. What bad things in theory can happen if we will allow requires auto only for constructors? Interesting questions? Write it down in the comments. And what is key feature of concepts and requires expressions? They do have partial order. Concepts are not just syntactic sugar. They carry semantic load and participate in overload resolution. The compiler can order overloads based on concepts, choosing the most specialized one. Whatever it means. We will now dive into what it means. Intuitively, most specialized one is the one whose requirements are the strictest. And this ordering, known as partial ordering, allows creating complex hierarchies of overloads where the compiler will automatically select the best option on the past arguments. Consider this example. This is ordered like A less than B shall exist. This is incrementable, like plus plus A shall exist. And this is like same with int. And we do have two functions. One is constrained with ordered or incrementable or integral. And second is constrained only with ordered. And we are calling foo from y. What do we see on the screen? Which is the most constrained one? And let us see the browser. Okay. So the most ordered here. This one returns 2. This one returns 22. We have some type, double type, and this returns 22. Why? Because this is the most specialized one. You see, it required to be ordered, and double is ordered. And this required to be ordered or incrementable or equal or int. Or ordered or incrementable or int. And this is definitely less strict constraint. And this is definitely a much better constraint, and you can see it wins the overload resolution process. Okay, and here the tricky stuff begins. How can it even work? How does the compiler understand that ort is more specialized than ort or some other like orto void or orto int or so on? And at the heart of this ordering lies the decomposition of a concept into atomic constraints and their subsequent analysis by the compiler regarding whether one constraint implies another or not. And what is atomic constraints? If we will have some composition of constraints with logical operators like logical or logical AND, atomic constraint is the single conjunct or single disjunct of this composition. And for those logical operations, even usual lazy rules are working. Because here, if size of t is satisfied and size of from int is definitely 4, then it is okay even if int have no column value inside it. Because, okay, this is a part of or is lazy, this is satisfied, all is okay. And when we can see the atomic constraints, we are now ready to study the subsuming rules. And the subsumes relation between concepts is formally defined by converting them to some normal form and pairwise comparing their atomic constraints. To be more formal, A constraint P subsumes a constraint Q if and only if for every disjunctive clause in the disjunctive normal form of P. Each element of this disjunctive normal form subsumes every conjunctive clause in the conjunctive normal form of Q. And how do you think? Q1 is Q or size of T equals 4. How the subsumption looks like between Q and Q1. And here P is Q and R. Definitely P subsumes Q and P subsumes R. So if we have a more specialized constraint, more specialized concept, it subsume it less specialized constituents. The key point on atomic constraints, this is another quote from the C++ language standard. Two atomic constraints are considered identical only if they are literally the same. Even semantically equivalent but syntactically different expressions are considered different by the compiler. For example, this is an example from the standard, by the way. We can have this inline variable, template variable, atomic equals true. And we have two concepts, C and D. And C have atomic of T, and D have atomic of T pointer, and true. And of course, C and D are the same. They are both true everywhere. But compiler cannot determine between D and C. If you will overload some function on C and D, this is ill-formed, no diagnostics required. And of course, in the ideal world, we would prefer this for subsumption. A constraint P subsumes a constraint Q if and only if Q implies P semantically. But we are not in the ideal world. We will say something about the ideal world later. And what drives me really nuts, that identical is not similar. It can really lead to surprises. Say you have two overloads with those concepts foo and bar that looks like bar looks subset of foo. For foo looks really more constrained. It is integral, and this integral is not concept. This is just integral v, and this is size of t more than 4. And I expect that this overload will be called, but this is compilation error. Because this is not a concept. To have atomic constraint participate in the subsuming operations, they shall be identical concepts. And what is even more inconvenient, subsuming is not automatic. If we have two concepts, foo, and we requiring function foo to exist, member function foo to exist, and bar, we requiring member function bar to exist. If we have some constraint that requires the conjunction of foo and bar to exist, this just not working. Because compiler will not divide this into real logical end of atomic constraints. And can you guess how can we fix it? Okay, this will fail, but I want this to win more constraint. I want this to win. And how can we fix it? 3, 2, 1. Okay, of course. Just have this concept, which consists of two concepts. And now subsuming works. And I can guess that standard committee made this just for you to write concepts. And to write simple concepts, and to write a lot of simple concepts, and combined combine a lot of simple concepts with simple logical ands and ors. This is my only suggestion. And let me show you the example, because it is really interesting example. You see, this is what I showed on slide. This is we are requiring foo to exist, we are requiring bar to exist, and if we are using foo bar and if we are using foo and bar, there's are two big differences, because say we have s foo and we have s bar, and if we have overload between this one and this one, overload with foo bar, then call is ambiguous. And if we will switch toggle this to 0, and now we have overload between this and this, and everything is okay. And this is really crazy for me, because what what is the problem here? What's the problem to make this into a conjunction? In the bibliography, I will have a great talk of Nico Yosiutis about. In this talk, he made some suggestions about why it is so. I will not repeat those suggestions because I really don't know. Okay, and now when we introduced the subsume relationship, we can create a hierarchy of concepts for iterators, because we have a concept input iterator that consists of concepts and requires expressions joined by and iterator concepts, and requires iterator category T, and requires derived from iterator category T input iterator tag, and the same forward iterator. And those requirements are not are not atomic, of course, because iterator itself consists of a lot of concepts. But if you will go down to atomic concepts and form disjunctive normal form and conjunctive normal form, and check subsuming, you will see that forward iterator subsumes input iterator. And based on this hierarchy, we can build function overloads, and the compiler will correctly choose despecialization for random access iterator, even if the argument also satisfied the requirements of input iterator. And now our overloading works. And we did a really long way for it to work. The power of this approach manifests itself when designing complex libraries. We can create specialized, highly efficient algorithms for specific categories of types, like random access iterators. You see, this is really efficient with just subtracting iterators, and maintaining general implementation for weaker categories like this one. However, this power comes at a cost. As Andrew Sutton, author of Concept Slide, noted, complex concept hierarchies can lead to unexpected problems and ambiguities for some borderline types. Sometimes it's simply and more reliable to explicitly list all desired overloads rather than relying on the automatic resolution on the complex hierarchy. And Sutton have some counterexample. Consider this copy algorithm and this copy algorithm with contiguous iterator here, and mem-copyable requirement. And try to guess if this subsumes this. And this is not so easy. And Sutton tried, and he failed several times trying to make this work. And in the bibliography, there will be a Sutton's talk, of course. And subsume relationship here is so hard, then Sutton just not sure that he cannot run into some unexpected issues for some types, because we cannot check for all possible types. It is like exhaustive testing. And Andrew Sutton thought a bit, and he He said, in some cases, especially when implementing highly optimized libraries, a direct approach with explicit checks like if const expr mem copyable might be preferable due to its simplicity and predictability. It's not always worth chasing maximum generality at the expense of clarity and readability. And Sutton said, after all, how often do we introduce new iterator categories? Because of course, you may say this is awful, this is intrusive. We are not nice. We are not allowing for overloads for other iterator categories. Okay, what iterator categories? And this is interesting argument. Please write in comments what do you think about it. Okay, and now we are close to finish, and let me show you the concepts we dreamed of, because concepts are known from like early zeroth and like 2003, I believe. Björn Strostrup and Gabriel Dos Reis published an article, and it is really interesting to look at history because the concepts were much more complex and included not only syntactic but also semantic requirements like axiom equivalence relation equal TT. This means that constraint, syntactic constraint equal, follows the equivalence relation rules like reflective, symmetric, transitive, and so on. And even more, axiom equality for any predicate p, x, and y, x and y, x equals y implies p at x equals p at y. Great. I don't even know how sensible compiler can check for it. You could do it in languages like COQ, I believe, but in enormous amount of time. However, the standardization committee deemed them too complex, and eventually we got the lighter and more practical concepts like now in C++20. Okay, and now, of course, some homework assignment. And don't be shy, write homework assignment in the comments. First task, please design realistic overload set for generic function and power using constraints. Account at least for integers, floating point, and matrices, and better account for like something even more interesting. And second is please explain what's going wrong here, because what I want to have, I want to have some concept that requires like collapsing and requires pack to be more than one element, and I trying to apply it here like this, and it fails miserably. You may see the compilation failure, a compilation error message on this link. Okay, and now some bibliography. Of course, you can understand first two bullets. I highly recommend you to read Alex Stepanov's book, Elements of Programming. This book really worth reading, and it is the definitive book of generic programming, I believe. Also, it is really interesting to see Titus Winter's talk and Andrew Sutton's talk on Concept Slide. Uh, Also, I can highly recommend you Nico Yosute's talk on the CPPCon 2024. And this is also really good and this worth looking. And of course, any talk and any paper and any book in this list is talk, paper, book I borrowed for this lecture. And thanks for all those guys to investigate this interesting area. And that's basically all for today, but I want to announce next time we will start the main part of the first half of our course. We will dive really deep, and we will dive into the name lookup and overload resolution problems, and we will introduce the notion of semantic process. And that's all for today. Thanks, everyone.